Hi there. Today we're going to talk about linearity and superposition. I'm Vivek Subramanian.
And I'm Michelle Maharbis. Let's get started. So linearity is a very powerful concept, and what we want to do in this little module is sort of spell it out for you formally, give you a procedure for how you can use the idea of linearity in solving circuits, and then work through a simple example. So first off, let's just recognize that mathematically a function f of x, a function which is a function of this input x or this variable x, is linear if this relationship holds. That is to say that if I multiply my input by some constant, feed that into the function, I'm going to get the same answer as if I had applied this input to the function and then just multiplied the result by a linear constant. This seems, like maybe a small detail to you. You may have seen uses of this in your mathematics courses. I would say that it's a good exercise to think for a minute what simple functions you might know that satisfy this relationship. It's a good little exercise to do for a few seconds. You're certainly going to see examples of this in the context of our circuits. Now, what we're going to assume in this class, unless you're told otherwise, and of course it is definitionally true for the components here, but we're going to assume that all the circuit elements are linear. Or, and this is a little detail with quite a lot of power, we're going to assume that they can be modeled by linear equivalent circuits. So let me clarify that a little bit, and then we'll go through a laundry list of example components we use. So many things are definitionally linear. Resistors have a linear relationship between voltage and current, which are the things we're interested in.
So let me see if I can take that resistor element and think about that function above. So what you're telling me is if I had a resistor and there was a current flowing through it and it was 5 times larger, I would get the same result if I just did the analysis for my original value and then multiplied by 5 at the end.
Yeah, that's right. I mean, that's essentially what you're saying. Because of the nature of this function and the VI relationship, it satisfies this condition. That's absolutely right. And we're going to exactly show you guys this in a minute, how easy that is. So
let's test that. So let's say I had a 1 ohm resistor and a 5 amp current. That says I should get 5 volts. Mm-hmm. I could do the same analysis by assuming a 1 amp current and then multiply by 5 at the end. That's true, because 1 amp times 1 ohm gives me 1 volt, and then I multiply by 5, I get 5 volts.
Exactly right. Yep.
So that's how you test for elements that would satisfy that linearity requirement.
That's right. And resistors are the most straightforward one, and that's pretty much all you've seen so far. So the other thing to point out is that sources can be linear, but of course it depends on how you define the source. So particularly with regards to those dependent sources where we can build any function we want, for example, a voltage-controlled current source, that current going through the source depends on a voltage somewhere, but it depends on that voltage by some function, right? I could say 5 times the voltage is the current, and so on. As long as that expression is linear and satisfies this, then we're fine. But of course, let's point out very clearly that you can take a dependent source and write, some completely nonlinear function for it if you wished, and then attempt to solve it. And that wouldn't satisfy necessarily the rule we've been giving here for linearity. For example, I could say that the current equals the square of some voltage somewhere. Capacitors and inductors are also linear, okay? And I'm just pointing this out now early, even though you haven't seen them, because you're going to see a derivative, and some students see the derivative and freak out and say, oh, it's not linear. So they absolutely are, okay? So having given you this, the idea now is to examine some principles and some theorems that apply if you assume the circuits are linear and that make your life a little bit easier.
Now, we should point out here one interesting thing that engineers often do. It's true that the analysis we've been looking at is related to linear circuits, but even if we have a circuit that is generally nonlinear, there might be regimes where it looks linear. And so provided we limit our analysis to those regimes, we can use some of the tools and techniques that we're going to learn here to analyze circuits that may generally be nonlinear.
Yeah, and that's often called linearizing. So for example, going back to the statement where it says or can be modeled by linear equivalent circuits, We often take things that are complex, as Vivek said, and we'll find some area that interests us where we think our circuit will be operating only in some particular regime. Like, for example, between 1 volt and 1.5 volts, we are not interested in the areas away from that window. And maybe our device that's nonlinear in a general sense operates pretty linearly within that window. That allows us to pretend that it's linear by linearizing it, and then we can use these same principles, of course, with the caveat that we have to be careful. Okay.
All right. So having introduced the concept of linearity, we now get to take advantage of a very powerful concept called superposition. And essentially, here's what we note. If a circuit, and we're specifically dealing with linear circuits, if a circuit contains more than one independent source, the response, and that could be a voltage response, a current response, of any element in the circuit is equal to the algebraic sum of the individual responses associated with the individual sources as if each had been acting alone. Let me explain what that means. Let's say I have a circuit that has 5 resistors and 3 voltage sources. And what I can do, based on superposition, is I can pretend I only had 1 voltage source, and I can figure out the currents through all the resistors. Then I can do it for another voltage source, and then for a third voltage source, each on their own. The net result of the circuit that would have all of those voltage sources in there would just be the sum of the individual responses.
I get it. So basically what we're going to do in a minute is take a circuit that has many sources, and in a sense, as long as we properly know how to ignore most of those and leave one behind, we'll be able to solve for the effect that that one has on the whole circuit, then go to the next one and the next one, and in the end we can just sort of add it all up. Is that right?
That's exactly right.
Okay.
And that is the basis of superposition.
Okay.
So now you can immediately see what the advantage of that is. The advantage of that is we can, rather than having a complex circuit that has multiple sources and sort of doing KVLs or KCLs to deal with all of them, we can simplify things by essentially dealing with one source at a time. That will hopefully make our analysis simpler. The trade-off is, of course, we end up doing multiple analyses for each instance where we've turned off one of the sources, but then we can combine them together at the end, and hopefully that makes life easier.
Sounds good. I think that makes some sense. So let's lay out a procedure and make it real simple so that we can go through exactly what Vivek just said and try not to make any mistakes. First of all, let's review. So if a circuit contains more than one independent source, the voltage or current that's associated with any element in that circuit is equal to the sum of the responses associated with each individual source as if it had been acting alone. So let's go through a procedure for trying to capture that when presented with a circuit. Okay, so first of all, the first thing to do is take your circuit and set all of the independent sources to 0. But let's think about what that means. This is where most students make a simple error in homework and in the midterms. By 0, we mean when you're presented with a voltage source, you're going to short it. In other words, what you're saying is that the voltage across the 2 nodes, right, is 0. That's a short circuit across the 2 nodes. If you're presented with a current source, you're saying that the current between the nodes is 0. So if the current between the 2 nodes that the current source is touching is 0, in that branch, you're going to have an open circuit. You have to be very careful, and I know I'm kind of overstating this, but many students will just sort of erase the source with an eraser or get rid of it. And if you just do that mindlessly, you're replacing everything with opens, and in some cases that's just wrong. You're going to get the wrong answer. It's not a question of erasing it from your circuit. It's identically saying that that function equals 0, that the voltage is 0 or the current is 0. So think about that when you're doing it. Okay? And you're going to do this for all of them except for source 1. And source 1 is any source. Just pick a source you don't want to get rid of and leave that one still running in the circuit, if you will.
So this is following up on the idea that we're going to do one source at a time.
That's right.
So you basically pick the one source, you leave that alone, and all the other sources you eliminate either by going to short circuits or open circuits.
That's right. And then once you've done that, you just solve for whatever it is you want to solve. Maybe all the node voltages or current in a particular place, whatever it is you're being asked to solve, with whatever analysis technique you like. based only on the contribution of source 1. And then what you're going to do is you're going to write your answer down somewhere, and then you're going to repeat this procedure for all the other sources. That means go back, turn off source 1, leave all the other ones off, and then pick, say, source 2, whichever that might be, and turn that one on. Leave it in its usual value, the value given to you in the circuit, in the original circuit, and then go ahead and solve again. So what you're doing is you're calculating or you're solving for the thing you're interested in for each of the sources acting independently. Once you have those solutions, you're just going to sum them up because of linearity. Oops. So linearity will allow you to sum them up, and in the end you get the total answer. And that will be as though you solve the whole circuit with all of the sources on at the same time, say with nodal analysis or mesh. You'll find that you get the same answer. So I think you just saw me skip ahead. Let's do an example.
Okay, so here's an example of a circuit. Now, let's point out up front, this circuit is pretty easy. So this is one you could solve just using nodal analysis or mesh analysis on your own. I mean, it's a trivial circuit to solve. But let's go ahead and do this by superposition. Now, first check, is this linear? Looks to be. I have a voltage source, I have two current sources, and I have resistors. So I should be able to do this by superposition. So now what I'm going to do is I'm going to leave the voltage source on, and I'm going to turn off IS1 and IS2. Now, Michelle, based on what we said earlier, what do we do with IS1 and IS2?
So what we want to do is say that the current IS1 equals 0, and the current IS2 equals 0. So if there's no current running through the node, basically ground, which is the node below IS1, to the node above it, you're left with an open circuit.
Right. So we're just going to make these open circuits. So we've made them open circuits. We've eliminated them. All right. Now look at this circuit. This circuit is pretty easy. R2 is basically dangling, is doing nothing. There's nothing on the end of the V1 wire. So it's just a simple voltage divider, and it's a voltage divider with R1 and R3. R2 no longer matters.
So you're saying R2 no longer matters because the independent current source now has a 0 current, so that means there's a 0 current running through R2, and so there's no voltage.
That's right.
Okay.
That's right. So therefore, this is just a voltage divider between the voltage source and ground, and the voltage divider is constructed using R1 and R3. We know, therefore, the voltage V1 is calculated for the case where we only have the voltage source VS1, so we call that V1 VS1, is just going to be R3 times the sum of R1 plus R3 times VS1. So it's a standard voltage divider equation. So we've now got our voltage V1 calculated under this condition. So now, Michelle, maybe you can do the next one.
Okay, let's see. So what I want to do now is pick another one and leave that one on while turning the others off. So let's turn off VS1 and let's turn off IS2. So what does that mean? Well, again, IS2 is going to be identically equal to 0. This is an open. VS1, the voltage from this node to the node ground is 0. So that's a short circuit. So what we're going to do is short. See, this becomes a short. That one, of course, we've left alone, IS1. And this is as before. Okay? So let's analyze this circuit. This is also pretty straightforward, right? This voltage here is essentially across the parallel combination of R1 and R3. So notice that R1 is to ground and R3 is to ground. So these two things are in parallel, right? And then again, this current going down R2 must then go through the parallel combination of R1, R3. And so it's a pretty straightforward exercise to calculate V1 because it's the current IS1 that's going through the parallel combination R1, R3. Fair enough?
Yep. So, okay, we're now on to the third part of our analysis. In other words, we have to deal with IS2. So, what are we going to do? Well, we're going to leave IS2 in place, and we're going to eliminate VS1 and IS1. Okay, so we've got to turn off VS1 and IS1. VS1 should, of course, being a voltage source, it should be a short circuit, and IS1 being a current source should become an open circuit. So we have a short circuit here and an open circuit here. Now what we're left with is a relatively simple circuit. We have IS2 driving into the parallel combination of R1 and R3. R2 doesn't matter since it's on an open. So therefore what we're just going to have is we're going to have the voltage appearing across the parallel combination of R1 and R3, and the voltage is just going to be IS2 into that parallel combination. So V1, when stimulated with IS2, is just going to be the parallel combination of R1 and R3 times IS2. So we therefore have finished our individual analyses. Okay, So now let's go ahead and put them together. So the overall solution is the sum of the individual solutions. So we put them together. We've got V1 calculated at VS1 plus V1 for IS1 plus V1 for IS2. We put them together, and we have a solution now that is the superposition of all of the individual solutions.
And we've cleaned it up a little bit for you and factored out. But if you go back and add them all up, you'll see it equals this. So what I like to point out here, and I think this is one of the take-home messages of this, is that some students see this and I think somewhat correctly say, oh, why would I do this? It's 3 times more work and so on. And as Vivek pointed out, we gave you a very simple example just to go through the practice of it. But this has a lot of power, and I don't want people to forget this. Imagine, for example, that we were dealing with a case where we have a much more complex circuit, and not only that, but their sources are qualitatively somewhat different. Maybe you have something like noise and then something like a superimposed signal. Once you get good at superposition and you know when to linearize or how to linearize, it becomes a very powerful tool for teasing apart different phenomena that are occurring in your circuit and actually acquiring qualitative understanding of how the circuit operates. I think it's a very, very powerful technique in analog circuit analysis.
That's right. The idea is you could now have one voltage source, which is a DC source, and another source, which is some other type of source. And provided we know how to linearize properly, we can deal with those.
That's right.